Hello everyone, welcome back to Geology and welcome to minerals. Minerals are very important when we're talking about geology, both on their own, because they are frequently in and of themselves resources that we'll talk about a little more here in a minute, but also minerals are what make up rocks. And so, as people who study the earth, rocks are very important to us. Now, geology is not the study of rocks, that's petrology. Geology is obviously the study of the earth, and we use rocks a lot, but we use other things too. So, the picture that you're seeing here, by the way, is of some gypsum crystals in a cave in Mexico. And that orange thing you see in the middle of the picture is a person. And so these are huge. These are I'm pretty sure they're the biggest crystals we know of anywhere. A gypsum crystal like that is usually about the size of, say, your pencil, and obviously those are much bigger. I mentioned. Oh, by the way, I'm not recording myself because as I looked through this PowerPoint, I realized that there's a lot of things in the lower right-hand corner that I want you to get a good look at, and I don't want to be covering those up with me. So just the PowerPoint today. So I mentioned minerals as a resource, and they are. I mean, if you want, for example, iron, you're going to need a mineral that contains iron, something like pyrite or something like that. If you want carbon, you're going to need a mineral that contains carbon, etc., etc. And this really comes into play a bit. Let me see if I can get to the next slide. Next slide. There we go. Here's a Navy SEAL or just a military person with all the gear that we carry nowadays, but then also the countries where the chemicals come from to make that gear. And you can see that it gets geopolitically very, very complicated when our military is relying on, chemicals from minerals that come from places like China or the Congo or South Africa or Mexico or something like that. And this is just a few. There's actually much more than this. And it's not just military gear. Your smartphone, the GPS on your smartphone, requires rare earth elements that we just don't have here in the United States. And so you can see how this would complicate things a lot geopolitically. I mean, you might want to just tell China to go, do something to itself, but then they go, okay, do you want night vision goggles and GPS? Because you're going to need that, galenium and all kinds of latium and all kinds of weird exotic chemicals that y'all don't have. And so the global supply chain really is global in this case. And so and in all of these chemicals, you don't just find aluminum laying around. You find the mineral bauxite, and then you extract the aluminum from it. And that's the way just about all of these chemicals are. Very rarely do you just find something laying around. Sometimes you do. Copper you do. But some things, most things you don't. Most things you find in a mineral ore that you then have to extract it from. And here in the United States, we have a lot, but we don't have everything. We don't have nearly everything, and so things get really, really complicated, really, really fast, actually. So in addition to being important to geology, let's ask ourselves, what is a mineral? Well, we have a 5-part definition, and you got to meet all 5 parts. If any one of these is missing, it's not a mineral. So, what are the 5 parts? First of all, naturally occurring. This excludes weird things that people make in labs and things like that, right? Now, we can make minerals in labs. For example, diamond is a mineral, and we make, diamonds in labs nowadays. But at some point, there are also diamonds just out there, laying around for people to pick up. So it is naturally occurring. Generally inorganic. And what I mean by that is it's not alive or living tissue or something like that, although that part of the definition gets really kind of weird sometimes, but and we'll actually talk about that here in a minute. But yeah, it's not alive, or it's not part of a living organism or something like that. Solid is pretty straightforward. Solid, as opposed to liquid or gas or plasma or something. So solid is good. Crystal structure. And what we mean by this is what I have over here on the right. This is the mineral halite, which you might just know as salt. The salt that you put on your French fries, NaCl. But those sodium and chlorine atoms are stacked in a very, very regular way, right? And that's what we mean by crystal structure. They're not all just mushed together, right? If I come here, we can see the crystal structure of halite, and then this is the crystal structure of quartz with the silicon oxygen tetrahedra that we'll talk about later on in the lecture. And so that's what we mean by crystal structure, is this internal, very regular stacking of the chemical elements that make up the mineral. There's a very I need some water. There's a very specific arrangement of things internally. That is that crystal structure, and that's going to give minerals the properties that we're going to use to identify them. Now, that internal stacking is frequently expressed in a crystal. Right, here are some halite crystals, but it doesn't need to be, and minerals aren't always these great big honking crystals. A lot of times they're just kind of mush, but internally they look like this, right? Internally, even if the halite that you're holding in your hand just looks like a ball of something, right? Internally, it looks like that. Internally, it's stacked very regularly, and that's what we mean when we say crystal structure. The other thing about minerals is they have a very definite chemical composition. They have a chemical formula. All right, halite is pretty simple, NaCl. This quartz ends up being SiO2, right? That pyrite that I mentioned earlier is Fes, iron sulfide. The gypsum crystals that you saw on the very first slide, CaSO4H2O. There's another mineral called anhydrite, that's just CaSO4 without the H2O. But they have chemical formulas. Now, they're not always simple. I have a bunch of them memorized, but not nearly all of them. But they do have them. Now, there is variation. You can substitute one chemical for another sometimes under certain circumstances. But mostly they have a definite chemical composition. If you go on in geology, you'll learn about solid solution series and things like that, where that variation occurs. So, sorry, I'm not dying of the plague. I just need some more water. Okay, so pretty good definition. Naturally occurring inorganic solid with a crystal structure and a definite chemical composition. Couple things that are kind of interesting. The generally inorganic always catches my eye. Because I'm a paleontologist, and paleontologists rely heavily on the hard parts of organisms, right? When you find a dinosaur fossil, you're not finding flesh, you're finding bone and teeth. Well, bone and teeth are actually minerals. Bone is the mineral calcite and aragonite, and teeth is the mineral apatite, which I've always thought was funny that apatite, you get the idea. But anyway, and so that kind of pushes the boundary of the inorganic part of the definition there. Paleontologists, we concern ourselves a great deal with the mineral properties of calcite and aragonite with respect to bone versus aragonite. I mean, you find a lot more teeth in the fossil record than you do bone, because that calcite and aragonite tends to break down a lot easier and a lot quicker than that apatite does. So we're kind of aware of that, and it's kind of pushing that part of the definition a little bit, but nevertheless, it is very real, and there it is. Solid is kind of interesting too. You wouldn't think it would be, but it is. Water is not a mineral, right? Because it's a liquid. What if I freeze it, right? What if I turn it into ice? Oh, wait, right? It's naturally occurring. It's inorganic. Now it's solid. and it has a crystal structure, right? I mean, a snowflake is kind of an external expression of water's internal crystal structure. It definitely has a crystal structure, and yeah, it's got a, y'all know the formula for water. It's H2O. So yeah, and yeah, water's a mineral, which is kind of silly. I mean, it's like, okay, I don't know, you're at the geologist party and haha, there's a mineral floating in my gin and tonic, or or whatever. But beyond just the party trick, geologists who study glaciers very concerned with how the mineral form of water behaves, and how it responds, and how it flows, and how it does all kinds of weird things. Water in general does all kinds of weird things. But so I mean, everything has a melting point, right? The fact that water's just, the ice just happens to be liquid at room temperature, doesn't really mean much. Everything has a melting point. It's just sheer dumb luck that water's is, where it is, or ice is where it is. So anyway, so there's our definition: naturally occurring, generally inorganic, solid, crystal structure, and a definite chemical composition. If that's what you got, you probably got a mineral. Odds are. Now, if that's the case, what's a rock? Well, that's interesting. A rock, and the definition sounds weird. A combination of one or more minerals. Now, I don't know. I probably need to rewrite this definition because it sounds funny. Because we're talking about a combination of one, which is not something you normally think about. So let's come back to that for a second. Let's talk about what I mean by a combination of minerals, right? And that's just what you see here, right? You've got granite, which is a rock. Granite is made up of several different minerals, right? It's made up of quartz. It's made up of hornblende. It's got a little bit of mica in it usually. There's feldspar in there. If it's the pink feldspar, it's a pink granite. If it's the white feldspar, it's a white granite. There's also a green feldspar that can make green granite, but it is a combination of minerals. In the case of granite, you can literally look at the rock and see the different minerals, right? There's a piece of feldspar. There's a piece of quartz. There's some of that hornblende, right? You can literally see the minerals. Now, what do I mean by a combination of one? Well, and I wish I had a picture, but that's okay. A combination of, what I mean by that is one mineral, but with a lot of impurities or a lack of crystal form, right? And the best example I can think of this is limestone. Right, we live in Florida, right? There's limestone all around us. Well, limestone is the rare rock that actually has a chemical formula, right? Granite doesn't have a chemical formula. The chemical formula for granite is going to depend on where I sample it. Okay, limestone, on the other hand, is CaCO3, calcium carbonate. If it was a mineral, it would be calcite. Okay, but it's not a mineral because it doesn't have a crystal structure. Right, it's just mush of calcium, carbon, and oxygen all stuck together. And so as such, it's not a mineral, it's a rock. Right, and there's a few things like that. For example, this halite that you see here, if it didn't have the crystal structure, it would not be halite. It would be rock salt. Right, I mean, there's a few things around like that. And when we talk about sedimentary rocks, we'll talk about them. But there are a few things that do actually have chemical formulas, but they don't have a crystal structure, and so they're not minerals. Right, remember, in order to be a mineral, you got to have all of these. And if you're missing this one, you're a rock. It's it's a combination of minerals, or it's a chemical substance or a substance that doesn't have that crystal form, right? Okay, so now we know what a mineral is. Now we know what a rock is. In order to talk a little more about minerals, we need to understand a little bit about atoms. Because we're going to talk about mineral properties, and those properties are going to kind of rely on understanding atoms. And so, in case you haven't had chemistry, and I'm sure you've all had enough to know this, that that an atom is made up of 3 subatomic particles: protons, neutrons, and electrons. Now, you're probably used to a picture of an atom looking something like this on the upper right here, where you have a nucleus of protons and neutrons, and then you have electrons going around the nucleus of the atom, kind of like planets going around the sun, except they're not all in one plane, and like that. Try not to think of it that way, because that's kind of not right, right? What you have is a nucleus and then a cloud of electrons around that nucleus. These electrons are so small and moving so fast, very near the speed of light. And they're not moving in these defined orbits like this. They're moving all around here. And so even if you only have one electron, that one electron is effectively a cloud around that nucleus. And this is one of the big conclusions or premises of quantum mechanics, is that you can really only cite a probability of an electron being somewhere. There's really no way to know exactly where it is, because it is so small and moving so fast. And by the way, that's what quantum mechanics is. It's not any of that other weird stuff that you hear about. So anyway, okay, or probably. But anyway, protons, neutrons, electrons. So protons have a positive charge. They exist in the center of the atom. Protons will determine what the element is, right? Hydrogen is hydrogen because it has one proton. If it has two protons, it's not hydrogen, it's helium. If it has three, it's lithium. As four, it's beryllium, etc., etc., etc. If it has 8, it's oxygen. So the number of protons determines what the element is. They have a positive charge. The number of protons is also known as the atomic number. Neutrons are the great neglected subatomic particle outside of geology. No one really cares that much about neutrons. Geologists, we care about them a great deal, and we'll talk about why later on in the course. But neutrons also exist in the nucleus of the atom. They do not have a charge, but they do have mass. You can vary the number of neutrons in an atom, and what you do is that when you do that, you're making different isotopes. For example, the oxygen that you breathe right now, that you're breathing right now, is split between O16 and O18. O16 has 8 neutrons, O18 has 10 neutrons, and you can breathe them in and out, and your body does not know the difference. Neutrons come into play in geology a lot. In fact, I took a whole course in graduate school in stable isotope geology, which is using different isotopes in minerals and whatnot to determine different things. We'll talk a little bit about it. We'll talk more about it though when we talk about radiometric dating, right? Because it is a mismatched number of neutrons and protons that causes elements to radioactively decay, and we will learn that we can use that to figure out how old a rock is. So most chemists never even think about neutrons, but geologists, we think about them all the time. And then orbiting, quote unquote, orbiting the nucleus in a cloud, even if it is just one, are electrons. Electrons have a negative charge, and you add or take away, electrons to change the charge of the atom. Now, it's a little bit weird because electrons have a negative charge. So if you take electrons away, the charge goes positive. If you add electrons, the charge goes negative. Okay, and this is going to determine what the atom will bond with and how the atom is going to behave in all kinds of different ways. So anyway, with that quick review, let's think a little bit about identifying minerals. Now, identifying minerals is not like identifying, let's say, birds, right? If you had me for earth science, you probably heard me go through this already, but if you see a bird and you want to know what it is, you pull out your bird book, and your bird book has pictures of birds, and you match the bird that you're seeing with the picture of the bird in the book, and that's what the bird is. Now, ornithologists everywhere are going to tell me it's a lot more complicated than that, and it is a little more complicated than that, in that it might be a very small detail about that bird, but basically that's what you're doing, is you're matching pictures. Okay, minerals aren't like that. Okay, mineral guides have pictures in them, but we don't use those. Those are just there to make it look pretty. Okay, and if you're in lab, I'm going to figure out a way to get you to identify some minerals, and we're not going to use pictures at all. We're just not. And so, don't ignore the what a mineral looks like. Now, with enough experience, you can start learning patterns and whatnot. But we don't identify minerals with pictures. We identify minerals with properties. Okay, now, so what are these properties? Well, okay, not color. And this is hard because color is something that we use for everything else. It's the first thing you notice, but yet it is the least reliable way to identify a mineral. If we look over here, I've got 5 bits of the mineral, and it's all the same mineral. Okay, this is fluorite, and you can see that it can be really dark purple, kind of green, kind of yellow, kind of light purple, kind of lighter purple. I mean, it likes to be purple, but different shades of purple, but also green, and it can also be clear. It can be all kinds of different colors, right? All of these are the same mineral, right? At the same time, if I look over here, all of these things that are different colors are all the mineral quartz. You've got clear quartz, you've got this purpley quartz, which we sometimes call amethyst. You got this dark quartz, which is a smoky quartz. You've got this kind of rusty colored, right there. I mean, there's all different kinds of colors. The trick here is that very small amounts of impurity can radically alter the color of your mineral. And so if there's just a little bit of something in there, a little bit of titanium, a little bit of iron, a little bit of magnesium or something, so sorry, didn't mean to switch the slide, then suddenly, your mineral is a whole different color. And so until you have a great deal of experience, you don't want to pick something up and rely on color. I was teaching mineralogy at Texas A&M when I was in graduate school, and and I picked up a piece of potassium feldspar, and I said, okay, this is potassium feldspar. It is very, very frequently this pink color, but it's also got this property and that property and all these other properties. Here's how you identify potassium feldspar. And on the test, I handed them a piece of quartz, and it was rose quartz, right? It was a little bit pink. And way too many people saw that pink and just wrote down potassium feldspar, while ignoring all the other things, right? That was my mistake. I shouldn't have given them the rose quartz, because that was wrong of me. But I wasn't trying to trick them. In fact, it's one of those cases where I tricked them without even trying to. It never occurred to me that they would look at every single thing that was pink and think it was potassium feldspar, despite having none of the other properties. So my point of all that is, don't get attached to color. Just really just don't. Okay. Okay, if I can't use color, what can I use? Well, you can use luster. Luster is quite fun, actually. Luster is the quality of the light that is reflected off of the mineral. And there's 2 basic kinds, metallic and non-metallic. Metallic luster is what you see here. This is the mineral galena. It's an ore of lead, and you can see that it looks like polished metal, right? This didn't get polished. You dig it out of the ground, and it looks like that. It looks like highly polished metal. The mineral pyrite also. I think I have a picture of some pyrite, but that's not good. Right, here's another one. This is the mineral pyrite. It also has metallic luster, right? So-called fool's gold, because really idiots confused it with gold. Here, I'll show you in a minute how to tell pyrite from gold. But anyway, so this is what we mean by metallic luster, right? It looks like polished metal. Now, don't confuse metallic with sparkly. Right, if you look at a mineral like a diamond or something like that, or quartz, right? Let me go back to my quartz, right? If I look at this and I see sparkly bits, that's not metallic. That's sparkly. It's actually called adamantine, if you want the real word for it. That's not metallic, right? Metallic looks like polished metal. Okay, and then non-metallic is everything else. Most minerals that you run across are going to be non-metallic. They just kind of are. Okay. Now, in the real world, we have a whole bunch of different kinds of non-metallic lusters. There's oily and earthy and greasy and vitreous and adamantine, and there's a whole bunch of things underneath non-metallic that we're not going to worry about. Okay, for our purpose, metallic, non-metallic works really well because there aren't that many metallic minerals. So if you get a mineral and you know that it's metallic, that narrows it down a lot right away. Okay, metallic minerals, oddly enough, frequently have metals in them. All right, this galena has lead in it. That pyrite has iron in it. Metallic minerals very frequently are valuable, but they're valuable by the boxcar load because they are important ores for all kinds of metals that we need. Another mineral property vaguely related to color is streak, and I've gone past this slide a couple of times, so maybe you've noticed it, but streak is a very, very useful property. Streak is the color of the mineral when it's been powdered. And so now you're going, oh great, I got to powder a mineral. Now, yeah, it's not that hard. You get a little streak plate. I got about 250 of them in my lab. They're not difficult to find or anything. In fact, all this is a little piece of unglazed porcelain. Okay, if you have some porcelain dinner plates or a porcelain vase or something, find a part of it that's kind of rough, and there's your streak plate. Assuming whoever owns the porcelain, whatever, doesn't catch you. But anyway, and then take your mineral and rub it on the streak plate. Now, don't be shy. Okay, and I know this is all online, so you're not going to actually have to do this. But if you ever do, don't be shy. People like to kind of take the mineral and just kind of brush it up against this. No. Push down and rub. Okay, and you'll get a streak, assuming the mineral is soft enough. We'll get to that here in a minute. But frequently you'll get a color rubbed off on that streak plate. That color is diagnostic, right? Here we have pyrite. Here's a better picture of it over here, maybe, right? This brassy kind of yellow mineral, but when you streak it, it streaks dark gray. Hematite is another mineral that is kind of brown in color, but it consistently streaks red. When the mineral and the streak color are different, we call that incongruent streak, and it's a very, very handy thing. This is one of about 20 ways to tell pyrite from gold, by the way. It really does take an idiot to confuse them. And so, so streak is very handy. Most geologists who are going to be encountering minerals in the field will carry around a little streak plate with them and just pull it out and use it right there in the field. It's very easy. It's not difficult at all. And you can pretty easily identify a few minerals in the field with the streak, and then also in the lab. So streak is very important, and it's a very, very useful thing. Streak is consistent, right? Where a small amount of impurity can radically alter the color of the mineral, the color of the streak is pretty dang consistent. I mean, I've had pyrite with all different kinds of colors, and it always streaks that dark gray every single time. Another thing that's useful, another slide that we looked at a couple of times, is the shape of the crystal. Now, don't confuse that with crystal structure, right? Crystal structure is purely an internal thing, right? That's how those atoms internally are stacked. Crystal shape is, okay, when I pick it up and look at it, what does it look like? Okay, that is different. And that can be diagnostic. Minerals will have one, maybe two crystal shapes that they like to grow in. And if you know that, you can kind of narrow it down a bit. Right here, two different crystal shapes for pyrite. It likes to make these cubes, and it likes to make these kind of, what is that? I don't even know what you would call that shape. But anyway, that shape. But that's only two. That's not so bad. Now, cubes, I mean, lots of minerals like to make cubes, right? If I go back, this galena makes these cubic looking crystals. This halite makes these cubic looking crystals, right? So and for that matter, fluorite makes cubic looking crystals too. And so, pyrite isn't the only mineral that makes a cube, but once you see it's a cube and then you see that it has metallic luster and you streak it, now you're narrowing it down. Right, you're not going to just go, oh, it's a cube, it's halite, when it looks like that, and has that gray streak and metallic luster and whatnot. So none of these properties will in and of themselves identify a mineral, right? It's always going to be a combination of them. So, but you learn some common crystal shapes, and that'll be very, very helpful. And there's a lot of crystal shapes out there. They could be fibrous or bladed or banded or cubic or prismatic. I mean, there's a whole bunch of crystal shapes out there, and we do have a system for technically describing them called Miller indices, where you give each crystal face and orientation and things like that. But we're not going to worry too much about that. But if you just kind of learn what the crystal looks like, that's a pretty good thing. That's a helpful thing. Another really helpful thing, is hardness. Now, hardness is a very, very misunderstood property. Hardness is the resistance of the mineral to scratching. And I say scratching, I put scratching in all caps here because people confuse this a lot. They think that it's, resistance to breaking or crushing or something like that, right? They think that if they can take the mineral and hit it with a hammer and shatter it, that it's not very hard. That is not the case, right? A diamond, the hardest mineral we have, 10 out of 10. You can see it over here. 10 out of 10 on the hardness scale. I could lay that diamond down on this table, take a hammer and hit it, and it will absolutely shatter. Okay, I could even hit it with a piece of calcite, which only has a hardness of 3, and it would absolutely shatter. And so it's not breaking, it's scratching, right? That diamond will shatter. Now, oddly enough, what it won't do is scratch. Okay, and that's what hardness is. It is resistance to scratching. And if you watch those CSI shows, or they mess this up all the time on TV, right? They think that because something is hard that it won't break. It'll absolutely break. Resistance to breaking is like tensile strength or something like that. It's a different property. Okay, hardness is scratching. So how do we measure it? Well, there's a couple different ways. And so you can see here, we most often measure it on something called Mohs hardness scale, which is a scale that runs from 1 to 10. And then we have minerals that are each of these hardnesses, right? And so 1 is talc, 2 is gypsum, then calcite, fluorite, apatite, orthoclase, feldspar, quartz, topaz, corundum, and diamond. Okay, so we have these minerals arrayed. Now, if you want to know, if you think about this, if it is resistance to scratching, then quartz will scratch everything below it on this scale, right? Talc won't scratch anything, but everything will scratch talc, right? Fluorite will scratch this, but won't scratch this, right? And so you can envision yourself putting together a little kit, or you could order one that had a mineral sample that had a little piece of talc, a little piece of gypsum, calcite, fluorite, apatite, orthoclase, feldspar, quartz, topaz, corundum, and probably not diamond, because who could afford the kit then? And diamond is 10. It's way, 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 way harder than corundum and 9. And that brings up an interesting point. This is not a linear scale. If we look over here, we can see, an absolute hardness scale. We can see that, it's pretty linear, but then we jump here, and diamond is way, way harder than corundum. Right, corundum is really only a little bit harder than topaz. Topaz is a little bit harder than quartz. The scale works pretty well, but then it just jumps, okay? And we don't honestly have much between corundum and diamond, but it just jumps. So this is not a linear scale, okay? But you could order a little hardness kit that would have each of these 9, common, easily obtained minerals. And you could carry that around with you, but honestly, if you do all the fun geologists, we're going to laugh at you, because you sit down the outcrop and you have something you don't know what it is, and maybe you pull out some orthoclase feldspar, and let's say the orthoclase feldspar scratches it, right? So you know that it's less than a 6. So maybe you pull out some calcite, and the calcite doesn't scratch it, so you know it's somewhere between a 6 and a 3. So you pull out some apatite, and etc. And you can narrow it down that way, and yes, you can do that. No one does that. Here's what we do. Carry a knife, right? We all, carry a knife, okay? Not an expensive one. Like I've got my good knife, and then I've got my hardness testing knife, right? Don't carry your good knife, carry your good knife, but don't use it for this, because what you're going to do is that knife has a hardness, most knives have a hardness of about 5.5, right? Pick the mineral up and scratch it with the knife, okay? If it scratches it, then it's below 5.5. If it doesn't scratch it, it's above 5.5, right? Just knowing that, just knowing above or below 5.5 can be very, very helpful. There are a lot of minerals on either side of that 5.5 that look an awful lot alike. For example, quartz is a very common mineral. Calcite is a very common mineral. They're everywhere. And so if you have something, and they look kind of similar, they're both frequently, once again, I'm going to refer to color when I told you not to, but they look pretty similar. They're frequently kind of light in color. They're everywhere. They fill in cracks. They do all kinds of different things. And so it's pretty easy to confuse them. But if you do have your handy knife, it will not scratch the quartz, and it'll scratch the heck out of the calcite. So just knowing above or below 5.5 can be very, very handy in the field. And that's usually as far as most of us need to go in the field. But with a little bit of experience, you can say, okay, yeah, it scratched it. Great. Did it gouge it like an insane amount, or did it barely scratch it, right? If it barely scratched it, it's going to be up here closer to the 5.5. If you gouged the heck out of it, it's going to be down here around, 1 or 2 or maybe a 3. Right? And at the same time, you could ask yourself, okay, it didn't scratch it. Was it close? Or maybe turn the knife sideways and scratch it with the mineral. Does the mineral gouge the heck out of your knife? You might be up here around an 8 or a 9. Or did it barely scratch it? In which case, you might be down here around a 6 or a 7. So, with a knife, like I said, don't use your good knife. With a knife and a little bit of experience, you can, in the field, narrow this down a lot. And probably get somewhere close to the mineral. And then take it back in the lab, and there's all kinds of fancy stuff we can do in a lab to determine hardness. But this is a very, very useful property. Okay, let's I'm 36 minutes in. Let's take our break, and then we'll come back and we'll talk a little bit about atomic bonding, and we'll wrap up the mineral. So I'm going to put 5 minutes of something in here. I haven't decided what yet, but don't fast forward through it. Just sit, relax for a few minutes, and then we'll come back and we'll finish this up. Did you take a break? I hope you did, because I did. Okay, so let's move on into the mineral property of cleavage. Only in order to get that, we need to get a little bit of atomic bonding, and so atoms are stuck together in minerals, and they're stuck together by atomic bonding. And there's basically three kinds. There's more. There's van der Waals bonds and hydrogen bonds and other things like that. There's fancy quantum bonds and things, but we really just need to worry about three: ionic bonds, covalent bonds, and metallic bonds. So ionic bonds. In ionic bonds, what's happening here is that the atoms are bonded together just because they have a different charge. That's all it is, right? So if I have a positively charged piece of sodium and a negatively charged piece of chlorine, then they're gonna stick together to make NaCl, to make salt. Right, and so, or if I have, I mean, you can go on and on, right? If I have I don't know, I'm trying to think of another one. A positively charged piece of calcite, a negatively charged radical carbonate, I can stick them together to make CaCO3, which is limestone, or in the case if it's a mineral, it's mineral calcite, right? So that's what's happening here. These things are just stuck together because they have a different charge. This is not a very strong bond. In fact, putting that mineral in water will probably just break that bond, right? You've all cooked with salt, right? You put salt in water and it dissolves. There are also, though, covalent bonds. And in covalent bonds, now the atoms are bonded together not because they have a different charge, but because they're sharing an electron. This is a stronger bond. Okay, because now there are maybe one, maybe two, maybe three, maybe more electrons moving back and forth between those atoms, and that makes a much stronger bond. Okay, so there is that, and then there are also metallic bonds, right? If we think about metals have some interesting properties, right? You can bend them and shape them into things. They conduct electricity, right? There's there's a few really interesting things that metals will do, and they do that because of metallic bonding. And I put a picture up here of metallic bonding for you, because you can see that what's happening here is these electrons, they're not just moving around a single atom or being shared between two atoms. No, they're moving all around this matrix, right? This is why this is why metals conduct electricity so well, right? Because electricity is moving electrons, and so it's pretty easy to shove electrons through a metal because those electrons want to move around all those atoms anyway. It's also why you can frequently form and shape metals, right? Because those electrons will allow that to bend without breaking because they're moving around there. And so metallic bonding is a very, very interesting thing, and it's going to give some of our minerals their properties. And so ionic bonds, the atoms are stuck together because they have a different charge. Covalent bonds, atoms are bonded because they're sharing electrons. And then metallic bonds, the electrons just move all around in this crystal matrix. And like I said, there's also hydrogen bonds and van der Waals bonds and things like that. But those are the three that we're going to worry about. And so this brings us to then the mineral property of cleavage. Cleavage is the tendency for the mineral to break along planes of atomic weakness, and the planes of atomic weakness are there because there's weaker atomic bonding, right? That's why I just went through that atomic bonding thing with you. So here we have a mineral, something like mica. Okay, and so you got these sheets. The crystal structure here is you have these sheets of sorry, not a mineral, but you have these sheets of elements, right? And they're bonded covalently in this direction. They're bonded by sharing electrons back and forth. But just because you're covalently bonded in this direction doesn't mean that you're covalently bonded in this direction. And so, in fact, in the case of mica, it is ionically bonded in this direction. So that's a very weak bond. So I can take a knife blade and just squeeze it right in there and get it to break into these very, very thin sheets. And you can see this is the mineral mica. This particular one is biotite. And you can see that that translucent sheet. It's not that mica is particularly transparent or translucent, it's that the sheet is so thin that light just passes through it. Anything that thin, light would probably pass through it. So that's cleavage in one, really good plane. And so when we talk about cleavage in minerals, we talk about, how good is it? This is perfect cleavage. This is like amazing cleavage, right? But that's only one direction through the mineral. Mica has one cleavage plane. A lot of times we'll talk about more than one. For example, if I look at this piece of feldspar, we can see that it's breaking flat here, and it's breaking flat here. That's two directions through the mineral. That's two cleavage planes, right? One there and one here. Now notice this side. It's rough, right? That's not cleavage. That's just breaking. That's just breaking. Okay, but the other thing to note here is the angle, right? We can see here it's breaking like this and it's breaking like that, and the angle in between them is 90 degrees. That's an important thing. If I look here at this piece of augite, we can see that that angle there is not 90 degrees. Okay, it's actually 120 degrees. And so the angle between cleavage planes, it turns out, is kind of important. Let me just go back here. So yeah, the angle varies and is important. Keep in mind that not every mineral has cleavage, right? The mineral quartz, for example, doesn't have cleavage. If you break quartz, it just breaks, it just shatters, okay? Which also brings me to, don't confuse cleavage with crystal faces, okay? Quartz, for example, right, makes, that really pretty tooth-shaped crystal, but if I break it, it just shatters. It is covalently bonded in all directions. There is no weak plane of atomic bonding. Now, a lot of times if you have a mineral, let's say this piece of halite here, okay, that's what the crystal looks like. It makes a cubic crystal. And if it breaks along those crystal faces. And that's actually pretty common, okay, but not always. Sometimes minerals, have one crystal, and when they break in a whole different direction. This also brings us back to the importance of the angle between the cleavage planes, by the way. So this is halite. Very common mineral. It is salt. It is literally salt. You could grind that up and put it on your french fries. It's salt, okay? Halite makes a cubic crystal, and when it breaks into cubes at 90 degree angles. So it breaks into very, very small cubes. If you have some salt at home, especially that coarser, like kosher salt, and you pour that out on a table and you look at it under any magnification at all, you'll see it's a whole bunch of little cubes. Now, another very common mineral, calcite, for example. Calcite calcite makes these crystals, but they're not quite perfectly square, right? That's not 90 degrees, it's actually 75. They're kind of a little bit cattywampus. And the trick here is that calcite and halite can look a lot alike. They can look an awful lot alike. They're both very soft, and they're both cubic, and they're both frequently white to clear in color. And so telling them apart can be a little bit tricky until you look at the cleavage planes, right? They both have 3 planes of cleavage, so they're both going to make a cube, right? And so, this is, let me go back here for a second. This is what one plane of cleavage looks like, one direction through that crystal where it wants to break flat. This is what 2 look like, one there and one there, and then that third one kind of rough. You can see it in real life there, okay? Same thing here, but at an angle. And then this is what 3 planes looks like, right? If you have 3 planes of cleavage, that makes a cube, okay? So calcite and halite both like to make somewhat cubic crystals, and they both break along the crystal faces. So how do you tell them apart? Well, look for that angle right there. right? That angle is not going to be 90 degrees. Calcite, it's like 75 something. I forget what exactly, but it's not 90, right? Halite is 90. Now, the other way to tell them apart is to lick it, right? This is salt. It's actually going to taste salty. Don't go around licking minerals unless you're pretty sure about what you're doing, because there's toxic stuff in minerals. So you can also, by the way, have 4 planes of cleavage. And give me 1 second. I'm going to hit pause, and I'm going to find us another picture here. Let me hit pause. Okay, I'm back, but I really wanted to show you guys this. So here is the mineral fluorite as it grows. It grows in these cubes. This one is kind of dark because it's zoned. It's got a little bit different chemical composition out here at the end. Makes a really striking crystal. But these crystals are cubes. Now, if I take that, though, and I break it, it doesn't break into little cubes. The cleavage planes are not the same as the crystal faces. What it wants to do, what it will do, is it'll break across those corners, and so that will give it 4 planes of cleavage. And so if I take this mineral crystal, and I'm very careful about how I break it, I can turn it into these little rhombs or little diamond shape things. And by the way, we commonly call this shape a diamond because the mineral diamond also has 4 planes of cleavage. And so if you're only going to cut a diamond where it wants to break to start with, you're going to get a shape that looks something like that. And so 4 planes of cleavage, right? If I have a cube, that means I've got 8 corners. If I cut off all 8 corners, that's 4 parallel sets of cleavage. And it makes these little rhombs. I don't think there's commonly any more than 4 sets of cleavage planes. And so as we think about cleavage, we can have, let me go back real quick. There we go. Let's go back to here. We can have 1 plane. We can have 2 planes at 90 degrees. We can have 2 planes not at 90 degrees. We could have 3 planes of cleavage, in this case at 90 degrees. Sorry, or we could have 3 planes of cleavage not at 90 degrees like calcite, or we can have 4. And so, sorry, I'm not dying, I promise. And so it's a very handy property. Not every mineral has it, right? Not calcite, sorry. Quartz. If I break quartz, it just shatters. It just shatters. Okay. Another interesting property I mentioned before when we were talking about hardness, tenacity, right? Tenacity actually is the resistance of the mineral to breaking. And there's a few different things we can say about this, right? First of all, if you just hit it with a hammer and it shatters, that's brittle. Okay, most minerals are brittle, but the reason I put a picture of some gold stuff up here is because gold is a mineral. It's one of the minerals that we call the rare earth elements, or that we sorry, but gold's a mineral, and if I hit it with a hammer, it bends, right? It could be shaped. We call that malleable, okay? Or maybe you'll bend it and it'll snap back, and we call that elastic. So there's a few different words that we can use here. Elastic is pretty uncommon, but let me go back, because if I was looking at you face to face, I would have a piece of this, a piece of mica. If you take mica and you hold it in one hand between your fingers and you bend it and then you let go of it, it snaps back into shape. Most things don't do that, right? I don't care how thin your piece of quartz is. If you bend it, it's just going to shatter. But some things are actually elastic. They will actually snap back into shape, especially if they're thin. So tenacity, sorry. I don't know how I did that. Sorry, guys. Let's go back here. Went too far. There we go. Keep your hand off the trackpad. Okay, so anyway, so tenacity is an important property, especially when you're dealing with these minerals like gold and silver and copper, that you just really do just find laying around on the ground looking like that. And so it's a very handy property in that respect. Another really useful property is density. right? How quote unquote heavy is the mineral? Um, now I say quote unquote because density isn't weight, right? It's not mass. It's how much does it weigh as compared to how much of it do you have, right? It's mass per unit of volume, right? Density is the difference between a brick of styrofoam and a brick of brick. Right, the brick, it might be the same size as your styrofoam brick, but it weighs a lot more. Okay, that's density. We measure it relative to water. Fresh water at room temperature has a density of 1. Most rock is around 3. So when you pick up a rock, that's a density of around 3. Every now and then, though, you'll pick up a rock or a mineral, and suddenly it's like, wait, whoa. This is a lot heavier than I would normally expect it to be. Maybe it's got some lead in it. That galena that we've been looking at has lead in it. It's kind of heavy. A lot of minerals have uranium in them or plutonium in them or something like that. That can be pretty heavy. And so, or maybe you'll pick it up and it feels kind of light. There's some rocks and minerals that are like that too, and so it's a handy thing. Now you can take it into a lab and you can, weigh it in the air and weigh it in the water and do some math and figure out, what the density actually is numerically. Okay, but most often we just use it. Oh wait, that's kind of heavy. That's got iron in it. It's probably one of these minerals, and then you kind of go from there. And so that's most often how we use it. You will sometimes hear density and specific gravity used kind of interchangeably. They're technically not exactly the same thing, but for our purposes, they are the same thing. So if you read specific gravity, that's density. Okay, there are some other interesting properties that we kind of lump together sometimes. Magnetism. Some minerals are magnetic. Magnetite is the one that comes to mind right away. And so a magnet will stick to it. And also, some minerals will disrupt compasses because they have their own magnetic field. And so that can be useful. Double refraction. Do you see in the upper right-hand corner of the slide, there's a piece of calcite laying over some words. And do you see how there's two versions of the words? That's what we mean by double refraction. When light passes through calcite, it gets split into two rays, if you will, coming out of the mineral. And so that's double refraction. And there's a particular variety of calcite called optical calcite that is clear enough to see through and will enable you to actually see that mineral property. Another one that's very important for us here in Florida is reaction to hydrochloric acid. Some minerals will dissolve in very weak hydrochloric acid. I mean hydrochloric acid that you can drink. Okay, we're not talking about very, very strong acid here. We're talking about very weak acid, but yet when you drip it on the mineral, it fizzes like crazy. Okay, and that's the mineral dissolving. And so now, why does this matter in Florida? Well, it matters in Florida because most of our bedrock, the overwhelming bedrock in Florida, is limestone. And limestone, while not a mineral, has the same chemical formula as calcite and will also do this. And so limestone will dissolve in very weakly acidic groundwater. And so as groundwater runs through our bedrock, it dissolves it away, making caves and springs and sinkholes and things like that, right? We're going to do a whole thing about karst topography, and that is all based on that reaction right there, where that very weak hydrochloric acid will dissolve limestone, and it makes a whole landscape that we live right in the middle of here in Florida. Conductivity, and I mean that with respect to electricity, right? Some minerals will conduct electricity pretty well. Piezoelectricity is kind of fun. Some minerals will vibrate when you run an electrical current through them. Quartz is one of these. You run an electrical current through quartz and it will vibrate. And it will vibrate a very fixed number of times per second. I honestly don't know how many, but it does. And this is how you build a quartz movement watch. If you have a watch and it says quartz movement, that doesn't mean that the gears inside are made of quartz. What that means is you have a battery and a little piece of quartz in that watch, and that battery will run power through that piece of quartz. That piece of quartz will vibrate a very fixed number of times per second, and your watch will use that to keep track of the passage of time. That's what a quartz movement watch is doing. It's relying on that mineral property of piezoelectricity. Okay. So those are the properties that we use, and if you're in lab, you're going to learn how to use them, although I haven't quite worked that out yet, but I will. So anyway, and so let's talk a little bit about mineral groups. So if we think about what the Earth is made of, it is now. When I say the Earth, I mean the solid parts of the Earth. Okay, it is mostly silicon and oxygen. Now, when I say oxygen, I don't mean free oxygen that you can breathe. Okay, I mean oxygen tied up in solid rock and mineral in the Earth. And so, if silicon and oxygen are the two most common elements in the crust of the Earth, or on the Earth, and they are, then it makes sense that those two are going to combine to make minerals, and they do. When we combine silicon and oxygen, what we tend to do, or well, we don't do it, but what these elements tend to do is they tend to combine to make something called a silicon oxygen tetrahedron. And here's one blown apart so that you can see that there's a silicon atom rather in the middle. 1, 2, 3, 4 oxygens around it. Okay, that is a silicon oxygen tetrahedron. They look like this because those oxygens they're not apart like that. They're stuck together like that, right? And so if silicon and oxygen are the two most common elements, they make this silicon oxygen tetrahedron, then it makes sense that that the most common minerals on the Earth are the silicate minerals, the minerals that use this silicon oxygen tetrahedron as a building block, and indeed they are. By far the most common minerals are what we call the silicate minerals, minerals that are made up of these silicon oxygen tetrahedra. We'll talk about these in a minute, but the non-silicates are basically everything else. Okay, and so all this iron, magnesium, sodium, calcium, aluminum, other all of that is either going to be in a different kind of mineral, or it's going to be incorporated in between these silicon oxygen tetrahedra. Now, the thing about these silicon oxygen tetrahedra is they bond to each other. So in other words, the next silicon oxygen tetrahedron might be up here sharing that oxygen. And then you might have another one over here sharing that oxygen. And so if you have a lot of this silicon and oxygen, these things will bond with each other, which brings us to silicate structures. Hooray, silicate structures. Silicate structures are one of those things that we're going to come back to a lot, because this explains a lot. This explains why these minerals tend to break down at the Earth's surface. These minerals tend to persist at the Earth's surface. These minerals tend to make less explosive volcanoes. These minerals tend to make more explosive volcanoes. There's a lot tied up in these silicate structures, and so we want to kind of make sure we get this right. And so once again, what happens is that these silicon oxygen tetrahedra will usually bond together in kind of one shape or another. Okay, now if you start at the top here, we have actually not bonded together, right? And so a lot of times you'll have silicon oxygen tetrahedra just floating around, and in the case of olivine, there's a lot of magnesium, iron, and individual silicon oxygen tetrahedra floating around there, making the mineral, in this case, for example, olivine. If they bond into a single chain, that makes the mineral augite. And don't worry about remembering the minerals, because I'm not too concerned about that, right? They can also bond in double chains. And for example, this would make the mineral hornblende. They could bond in sheets. Remember when we were talking about sheets of minerals, and we were talking about micas, biotite mica or muscovite mica? Yeah, the reason they break with that cleavage is because the silicon oxygen tetrahedra are bonded into sheets, and the chemical bonding in between the sheets is very, very weak, and so it tends to break in this, in these planes. And then we have like, and it's always, no one draws this well, but if you have a three-dimensional network of silicon oxygen tetrahedra, they're all kind of bonded up to each other. That makes the feldspar minerals, which are very common, and also makes the mineral quartz, which is also very common. When we learn about Bowen's reaction series, when we talk about igneous rocks, we'll learn that, if I have a magma and I'm cooling the magma, these simpler structures are the ones that cool out of the magma first. These more complicated ones are the ones that cool out of the magma last. If I'm going to melt the rock, these are going to melt first, and then these are going to melt last. They're chemical resistance. These down here are very persistent in the environment. They're everywhere. If you go to the beach, it's pretty much all quartz, by the way. If you go up into the mountains, you get more of this stuff. You go, you get more of this stuff. So these tend to break down chemically very quickly. These tend to break down more slowly. And so there's a lot here that we're going to come up on later on. When we start talking about chemical and physical weathering, when we start talking about volcanoes, there's all kinds of stuff here that's going to play into this. So we'll be seeing this again. These silicate structures are very important, and they explain an awful lot. Last slide. The non-silicate minerals. Now the interesting thing is that these are the ones that are usually very valuable, right? We frequently call these, the silicates, the rock-forming minerals, okay, because these do usually make rocks. These are not rock-forming minerals, right? You don't find halite, fluorite, and hematite making a rock. You find these laying around as minerals. These are a lot less common than the silicate minerals, but these are the ones that you look for. No one goes out and mines augite, okay? You just don't, okay? It's, people mine quartz because of that silica, and you need it to make computer chips and stuff like that. But most of the silicate minerals, you don't go out and mine those, right? These you do. There are like carbonate minerals, for example, calcite and dolomite, halides, halite, fluorite, sylvite, oxides, hematite, magnetite, corundum, and then they list ice here as an oxide mineral, which it is. But look over here. This is what we use them for, right? Steel making, fertilizer, iron ore, gemstones, and an abrasive, lead, or zinc, sulfuric acid, copper, mercury, plaster, drilling mud. These are the minerals that we look for because they're valuable. We can use them for things, but they're not very common. Right? This is the realm of the economic geologist, right? This is the realm of resource geologists who are out there looking for and finding us the minerals that we need to make the things that we have come to rely on, right? We don't usually go out and look for these. They're usually parts of rocks, and silicon and oxygen, are very, very common. So it's not like it's hard to find that. This other stuff is less common, and that in a lot of cases, that's the stuff that we need. Okay, there's minerals. Hooray, minerals! I'll get this up for you guys. And next will be igneous rocks. Alrighty.